In this episode, I'm gonna walk you through linear and LDO hardware design guide, how to use these devices, what they are, and how to deal with them in PCB using KiCAD. So let's get started. But first, what is a linear voltage regulator anyway? Basically, this is the basic diagram of the linear regulator. It's a device that takes an input voltage and reduces it and regulates it to a certain output voltage. For example, from 12 volts to 5 volts or 9 volts or whatever. So it can reduce the voltage but not increase the voltage. And it keeps it regulated. Basically, if it's a 5 volt, it's going to continue to be 5 volts in all of the load situations. But this is the basic design of the linear regulator from the inside. It has basic elements such as the pass element, which is a transistor, an error amplifier, which takes a reference voltage of some sort internally generated and takes a feedback from the output through the feedback network and produces the necessary output to control the pass element in order to keep the voltage regulated exactly as you want. So it works by dissipating heat inside the pass element in order for the regulation to happen. So if I have like 10 volts in the input and 8 volts at the output at 1 amp of current, that means a 2 volts difference between input and output. 2 volts times 1 amp, that means 2 watts. So this series pass element, internal pass element, will have to burn 2 watts of power in itself in order to provide regulation. Basically, you can find this similar analogy happening in multiple data sheets or explanation blogs. The series pass element or the linear regulator as a whole will work as if it is a variable resistor or more like a voltage divider like this. Basically, current flows in and flows out of the series resistor or the resistor block that we drew right here, and the remaining difference of the power, it's burned inside of it as heat. And because of that effect, we can conclude that the internal transistor of the linear regulator is working in what's called the ohmic region. If you know your transistors, BJTs and MOSFETs, there is the ohmic region or the linear region. Okay, so it will be working inside of that region and not outside. So basically, if it is an NPN or a Darlington or something or a MOSFET like this right side figure, basically this is gonna be the linear region that it's working on. So this error amplifier will output voltages to the gate of the transistor or similar, which revolves around these particular values right here, based on, of course, the output voltage. And that's the basic reasoning after naming it a linear regulator. And as you notice that heat is a very big element when it comes to the linear regulators because of this internal heating situation, which we will need to talk about in the future of this video. When you start to design linear regulators, you're going to be basically faced with just two types, basically. The fixed type and the adjustable type. The fixed type is basically fixed output, like 5 volts or 9 volts or something like that. You cannot change its output, but you can basically control how the input works. You can put input and output capacitors for it, and so on. The adjustable, as you see, it puts the feedback block or the feedback network of resistors outside the chip itself. So you as the user, you will have to put these and you control them and you calculate them, as I will show you in the future of this episode. But for basic usage, the linear regulator, which is 5 volts, for example, if you want 5 volts, there is no reason to get the adjustable one, just get the fixed one. And as you can see, it is a very simple device. For example, this one is inputs, outputs, and basically ground, 3 legs terminal. Input and output capacitors are nearly in all regulators a must for stability and for best practices as well. But this adjustable part, it has, instead of the ground pin, it has the adjust pin, which is you should be hooking up the feedback resistors. Some adjustable ones will have a separate ground and a separate adjustable or feedback pin. Some of them both fixed or adjustable. They have something like enable pin if you want to enable or disable the entire regulator. They might have like power good pin, which sends a signal that if power is good and everything works fine, it sends a signal. Maybe if you need an LED indicator, basically many other variations that gonna happen, but basically this is the configuration that you'll be faced of. A big thank you to the sponsor of this video, PCBWay. PCBWay is the leading manufacturer in China for PCBs. They produce extremely high quality products with relatively cheap prices. They can do like PCB manufacturing, assembly, rigid flex boards, etc., as well as 3D printing and CNC machining. You can upload your Gerber file and then check your options, there are many of them, and then proceed with your order. Check the link down below. PCBWay is my manufacturer of choice for my highly successful and premium quality products, such as Thunder PSU for Dreamcast. They make the boards, source the materials based on my instructions, assemble the PCBs, and finally ship them to me. Basically, a one-stop shop for bringing your product to market and a long-term partner in success. I highly recommend you check them out for your next product or project. Their website link is in the description down below. So after this big introduction, what is an LDO anyway? Like you keep hearing LDO this, LDO that. So basically there are what we call the standard linear regulator and the low dropout regulator, which is the LDO. So we can talk about the dropout voltage, which is basically the difference between inputs and outputs, as I explained in the previous section of this video. For example, the 7805 requires 2 volts of the dropout, but as you can see here, I'm running it for like from 12 to 5 volts, which is basically 7 volts difference. And the LM317, depending on the manufacturer, requires 3 volts. But if you run it above 3 volts, it's gonna be fine. But under 3 volts, it's not gonna be fine, and it will never do the regulation that you want. So that's the importance of dropout voltage. 7805 can deliver 5 volts if it has 7 volts or more at the input. But if you go to something like this MCP 1700, it requires 340 millivolts of dropout voltage, which is very low. But this part, for example, it is rated for like 250 milliamps, so it's not really a high power device. But this part from Richtech is very expensive and very advanced. It is an LDO which has mere 90 millivolts of difference. It requires 90 millivolts to deliver 2 amps of output current. That is very low. But this is also like the 1117, very famous 1.3. This part from analog 130 millivolts, which is very low. And this part from TI, it is about 100 millivolts, similar to this one. We can say that it is a linear regulator, simple linear regulator, but with very low dropout voltage requirements. That's basically what an LDO is. But essentially, you're gonna deal with it exactly the same as a standard linear regulator with very few specifics involving stability, which we're gonna take a look into. So, which begs the question, like, how low can it be in order to be considered an LDO? You're gonna find lots of opinions and discussions, but basically that's a trivial question. We don't really need to have a definitive answer. But generally, people consider anything less than 1 volt of dropout voltage to be an LDO. This is a further explanation of the LDO. Internally, the LDO is basically made of MOSFETs instead of NPNs or BJTs in general. And it uses these type of features in order to get like really low dropout requirement, while the Darlington NPN used in many classic linear regulator, by design, inherently it requires higher dropout to operate correctly. Okay, so let's take a tour of the datasheet of the famous 7805 regulator. For example, this tells you that it has multiple packages on the first page, and the currents capability up to 1.5 amps, because not all revisions from all companies allow this. Some of them only half an amp, and it has like multiple variants. All of them are fixed, of course, because 78, then 05 for 5 volts, 06 for 6 volts, and so on, and some other features that you may or may not be interested in. Getting down here, we see the block diagram with internal series pass element error amplifier. As we explained, it has thermal protection, for example, as an addition from the company. This is the pinouts, so you can use it on your PCB design. And this is the internal die of the device. You don't really need to understand or even look at this if you want just to use it. Now we get to the ratings of the device. This is the maximum things that it can tolerate. I don't really recommend that you go that far, but rather go to the electrical properties we're going to talk about next. But it's good to know what are the absolute maximum you can tolerate. And this is one of the most important tables in the datasheet, which is the thermal data. These are called thermal resistances of the device based on the package that you are choosing, like TO220, D-Pack, D2Pack. We're going to talk about this in the next section, so I'm going to pass it for now. But it's very important. Typical application circuit, as we explained, input capacitor, output capacitor. They are telling you the minimum values you need to worry about. And basically that's all about this device. Getting down, we need to see the electrical characteristics. It is extremely important to look at these things. It tells you that it has the output voltage of 5 volts with some tolerances here and there based on load and temperature. Now, the load and line regulations basically means the line regulation, how well the regulation of this output of the device is done according to the changes to the input. So meaning if the input voltage changes or fluctuates, how well regulation is maintained. Okay, load regulation is the opposite, how well the regulation is made and maintained if the load itself changes. So basically these are the less the better, but don't really need to worry about this too much. Quiescent current, on the other hand, means that it is the current the device consumes in order to be fully operational. It tells you right about 5 milliamps or so. Not so big and not so small. Because if you have a battery powered device or something very, very low power, this thing is not really optimized for that. But if you go to the MCP 1700, which is, as it says right here, low quiescent current LDO, you go and check the data sheet, it tells you it has a quiescent current of a maximum of 4 microamps, which is absolutely low. If you really worry about power usage of the device and you want to enhance it to the best of your ability, then MCP 1700 is your choice, not the 7805. Next thing that you need to worry about is what's called the dropout voltage. That's the thing that you need to check in every data sheet of any part that you want. It tells you that the output current is 1 amp and the temperature is 25 degrees. It will be about 2 volts, as we explained earlier. Basically, you don't really need to design it to be like that precise. Maybe 3 volts will be a safe bet. Okay, and be sure to read some notes right here, because something like this minimum load current for regulation is 5 milliamps. So if it is like without any load, it may not regulate well. So maybe put a constant load or something on this. For adjustable power regulators, beside the linear ones, the fixed ones, you're gonna find this called the Vout setting equation. Basically, it tells you how can you determine the output voltage, which resistors should you choose. So for this LM317, this is the equation. V output equals 125, which is the internal reference voltage, multiplied by 1 plus R2 over R1. This is R2, this is R1. You can calculate it and maybe rearrange the equation so that it has the R2, for example, to be solved. And you can assume R1 from your side. Now, if you read the datasheet further, you can realize that R1 shouldn't be more than 1 kilo ohm for this regulator to work properly. Basically, anything lower is better. So for me, for example, I wanted like 9 volts for a certain application. So I can get this equation right here after rearranging it and say that I want 9 volts, which is times 125 minus 1 times the R1, which I assume to be 120 ohms. I get 744 ohms. So if I put 120 here, 744 here, I'm gonna get a really precise 9 volts output. But this equation is not constant for all other regulators, because maybe this Richtec one has an internal reference voltage of 0.8. Some of them has 0.6, some of them has 1. So basically you just dig in the data sheet. Checking this electrical characteristics of this very expensive Richtec device, we can see the input-output differential somewhere in here, and the maximum operating voltage range to be a maximum of 6.5 input voltage. The feedback 0.8 as I explained, and you can go to the dropout voltage right here at the 2 amps load. It's gonna be a typical of 34 millivolts and a maximum of 90 millivolts. So if you design it based on 100 millivolts, for example, that's gonna be absolutely fine. But of course, the quiescent current isn't gonna be like really nice for this device, because it's not made for that. One thing to mention that LM317 has a online calculator, for example. If you want to make it easier on you because it's a famous device, you can put, for example, 10 volts right here and let's say 240 ohms R1. It gives you like 1680 ohms for the R2. Basically, you can use that to determine the input-output voltage and the feedback resistors. One last thing I'd like to mention is that somehow the features of the device, for example, can be all laid out in the first page, but the details comes after it. One thing I really want to note is what's called the power supply rejection ratio, which is basically means how well the linear regulator reduces the input noise. This tells you that it is an ultra-high power supply rejection ratio of 43 dBs at 500 kilohertz. An excellent noise immunity, for example, this is the figures that it achieved, but you have to get in your head that linear regulators actually use all of these nice figures only at relatively low frequencies. For example, if the noise that you've got is like 1 megahertz, 2 megahertz, pretty much it's not gonna do anything for it. But if it's like 1 kilohertz, 50 hertz, something like this, 10 kilohertz maybe, yes, the linear regulator or LDO will do a really good job about it, which is why it is always preferred to use this type of device for sensitive applications such as analog to digital converters and whatnot. Of course, you have to stay in the datasheet to read about stability. This tells you that stable with 47 microfarad or larger ceramic output capacitor. See, it tells you exactly the device that it needs. But ceramics, of course, has like DC bias, and you have to account for that. Some of the old devices requires not just ceramics but electrolytic capacitors with reasonably high ESR so that it can get into stability. But modern devices, I read that they are fine with the very low ESR ceramic outputs, so you can use that. How can you determine which type of capacitor and which value? Basically, you need to just read the data sheet and see what does the manufacturer actually tells you about their device. Another table that you can find is what's called the feedback resistor values. Instead of you going through the equation and calculates it like this, it tells you like, hey, these are the standard output voltages that most people desire, and these are the recommended resistor dividers that you can choose, basically R1 and R2. For example, if you want 3.3 volts, you can just get 11.8 and 3.74 kilo ohm resistors, and that's all that's gonna be done. Basically, you can use that. For example, for external components, the capacitors, inputs and outputs, this is a part number that they recommend, and telling you that effective capacitance derated based on voltage level, etc., that I explained. But as a designer, you can basically use anything that you deem suitable after you know exactly what you're doing. So let's talk now about the thermal design of linear regulators. Now you can be faced with these equations as you see here in pretty much all data sheets. And this table is one of the important tables that you need to understand. Basically, this device offers you these types of packages and tells you the thermal resistance of each one. The junction to ambient and junction to case. Junction to ambient is when you never use a heatsink of some sort, and junction to case is when you use a heatsink. But basically, you don't need to worry about heatsinks for now. We just want to focus about the device by itself. First of all, you need to know the dissipated power inside of your device using this equation. And then after that, you can calculate the junction temperature based on this equation. So let's go for this example. You have 200 milliamps of this mysterious linear regulator, and input voltage is 9 volt, delivered to output as 5 volts. And the package is TO220, which is this one, okay, without a heatsink. So the dissipated power is calculated to be 0.8 watts. For a mere 200 milliamps, you're gonna almost 1 watt, which is crazy. So the junction temperature is calculated as the dissipated power times the junction to ambient resistance, thermal resistance of this package that I'm using, which is TO220, which is 50 degrees per watt. And the result is, after combining it with the ambient temperature, assumed to be 25, it's going to be about 65 degrees. Now, I put it in green because the device tells you in this datasheet that the maximum junction temperature is 125 degrees. But 65 degrees is not really that low for itself. But for the device, it can work perfectly fine with it. Let's assume that we run 1 amp of this device on these configurations. It's gonna heat up to 225 degrees, which is a lot more than 125. Therefore, it will burn and get broken and cause a catastrophe. So the thermal resistance is very important. It means that for every watt you dissipate in this device, in this package, it's gonna raise its temperature by 50 degrees. Which is not really cool because that's very high. But for example, the junction to case temperature, if you put a heatsink on this device, all the heat that's gonna be transferred from the device or the junction to the heatsink is gonna be very efficient, because look at this D2 pack, this one, very, very big package. As you notice, the bigger the package, the more heat it can dissipate, and the better transfer it can do. So it will almost transfer all the heat from the junction to the heatsink, and then you can worry about heatsink calculation later on. But that is a thermal design complete story of itself. We don't really need to go through that in details. But get it through your head that if you really need a heatsink, then you probably shouldn't be using a linear regulator anyway, or maybe you're using the wrong package, wrong design, and so on. I'm talking about normal low power devices, but not that very, very high devices that can require a heatsink by definition. But if you go to an LDO, for example, this expensive rich tech that I talked about, you can find this table similar to the previous one. It tells you that the package is WQFN, which is this one. As you notice, it has a what's called a power pad inside underneath. This is usually connected to the ground of this device. Now, when you put it on the PCB, you connect it to the huge ground plane that you already have through lots of thermal vias down to it, and it will transfer the heat efficiently to the ground itself, which will act as a heatsink. And that is a very important feature of such packages. Look at this, for example, the junction to ambient, because all of about itself is 54.8. It's very high. And look at this, the junction to case, or the bottom, it's gonna be 16.1, a lot lower than this. Junction to board may be something like this, because if I use the example that I talked to you about, then some of the heat will stay in the package because the thermal resistance isn't like 0 or 1, but a lot of it will be transferred down to the board. So this heat, this package may not be like very, very hot, but it will transfer the heat efficiently. So let's look at the example without a heatsink, without connecting it to the board, without anything, just by itself using the default configuration. 2 amps of output, 5.5 volts of input, which is very close to the 5 volts output, so merely half a volt difference. It's going to dissipate 1 watt. So if you revert back to this example, 200 milliamps of output current nearly dissipated 1 watt because it's a standard linear regulator with a huge dropout. But this one, at 2 amps, almost 10 times the current, about 1 watt of difference, which can result of about 80 degrees of heat, which is fine by the device, by the way, because it can operate at this temperature, which is less than the maximum of its internal die. But for you as a designer, such a heat generating source is bad. But look at this. If we put 5.1 volts input instead of 5.5 volts, it's gonna be 36 degrees, which is very, very, very low. This is almost as nothing is happening. It's almost like an ambient now. Now, how can you get like 5.1 volts? Basically, put a buck regulator or something like that before it to drop the voltage just before its internal dropout voltage kicks in, as we explained earlier. But if we have 5.1 volts input and 200 milliamps output, it's going to be mere 26 degrees, which is just 1 degree of heating from the current above ambient, which is fantastic. So this tells you that these LDOs are very efficient if you use them carefully and use them the way they are ought to be used. But pay attention to the thermal design before you dig into the PCB layout, before anything. Make sure that your device is correct and it's nice for the application. Go through all of these equations and determine which part to be used. Okay, so let's start by designing a simple circuit around 7805 regulator. This is the regulator itself, inputs and outputs caps as we explained. The input capacitors, I chose 10 microfarads and output capacitor also 10 microfarad. It tells you that you can use it without output capacitors, but the best practice is to use an output capacitor. And I also recommend putting a small size like 0402 and small size input capacitor like 100 nanofarads to be like very, very close to the input pin, as we will see right in here. For example, this is the layout. This is the input capacitor that I talked about, the small value, directly at the input, from input to ground, to short any high frequency noise or transients or something like that. This is the input capacitors. Basically, they need to be as close to the output to the input pins as possible, like this. And the output capacitor is also as close to the pin as possible. Maybe you can put it right here, for example, or maybe here if it fits. These are 0805 capacitors, so they are a little bit on the bigger side. Beside that, input and output power, if your layout allows it, you can use polygon pores instead of, like, for example, routing it like this, because polygon pores are low resistance and very nice connection between the pads. And for the ground pins, as you can see, you put multiple vias to stitch the ground from top layer to the bottom layer. And you can see it here in 3D. It looks fairly simple like this. This is a very simple device, doesn't really require any more attention than this. And basically you can, if this is part of your circuit, you can basically route the 12 volts using the polygon to the source, and you can basically take the output either from this cap using a very high trace like this, or also extend the polygon pore to wherever you want to go. As for LM317 adjustable regulator, this is the basic circuit that I went with: the capacitors at the input, the capacitor at the output, and the feedback resistors as explained. Now if I go to the data sheet, I see the output voltage to be set like this, and I rearranged the equation and solved it out. Very basic, and I got these values. Now if you go to the PCB design, this is gonna be more clear. As you can see, I went with this package. This is the output capacitor. These are the two input capacitors. Look at how close they are to the pin. Basically, the silk screen need to be moved. And the output resistors, it is important to lay them out to be extremely close to the feedback pin. But when you take the output from the output side and deliver it to the feedback resistor, which is this node right here, then you need to take it basically not from the output pin itself, but from the point of load. Let's call it that, the point of load after all the capacitors and just before it gets out to your circuit, because you don't want to basically take it from here and some drop voltage happens right here and gonna ruin your value. And of course, if your load is maybe something very far, it is always recommended to take it just before you want to get to your load, so that it compensates of the inductance and the dropout voltage that can or cannot happen during the layout. And the feedback pin, look at this. It is the feedback trace is a thin trace coming from here, separate from the output, so that maybe you do not take it like directly from here, something like this. No, I take it from the polygon pore, a very small and tight layout. Now this feedback trace, it must be away from all noise generating devices, such as switching regulators and stuff like that. So that's a very nice tip. Now notice that this 9 volts output, I used a polygon pore on both layers in order to use these thermal vias to transfer the heat from the output regulator down to this very small and can be a lot bigger heatsink, basically. Polygon pore used as a heatsink. Now, since these are a little bit close, they can be okay, but if you want the best thermal performance, then you need to put these basically inside the pad itself. You need to modify the pad and put these inside, which will transfer the heat more efficiently down to the internal planes. But of course, this comes with a big downside, because now you have to modify the solder paste so that it doesn't overlap with these holes, which makes it like dip to the other side. And it will maybe make it stick a little bit less than if it's like a big like solder paste layer. So basically that's about it. It's all about you testing what's gonna happen to you. For example, if you can put something like this all the way, maybe something like this. See, this is gonna be more and more efficient in transferring the heat. So I thought of just showing it to you. This is the 3D design. Nice and compact layout. Okay, so we talk now about practical implementation. This is one of the early prototypes of one of my upcoming products I made. I needed a 9 to 12 volts rail, so I used an LM317, as you see right here. See, this is the input capacitor, and that is the output capacitor. This is a 120 ohm resistor, as well as these two here, small here, are another feedback resistors, because they are gonna be switchable between 9 and 12 volts. So I needed the upper resistor to be switchable, but basically the same thing. And as you notice, I put a lot of thermal vias around this device from all directions, especially from here. These are the inputs of 15 volts, and all around here are basically another type of thermal vias connected to the output. So these are thermal vias for the input. These are thermal vias for the output. So what are the advantages and disadvantages of linear regulators and LDOs? So you can know where to use them and where not to use them. First, they deliver low noise output, as we have said before, especially in relatively low frequencies. They are very simple to design. As you can see, basically just input and output capacitors and feedback resistors if they are adjustable type. And that's pretty much it. They use small number of parts and they are low price, of course, relative to switching regulators. And one of the advantages that I like is that they are made by many manufacturers, especially the famous designs like 7805, 1117, something like this. They are made by many manufacturers, of which are the very, very cheap Chinese ones. But for the disadvantages, the very first one is gonna be the generation of heat, or namely the low efficiency. The low efficiency, for example, if you have a battery powered device and you do not have like a buck regulator before the LDO will waste a lot of power. May not necessarily generate heat because of that, but of course it's gonna waste a lot of precious power. And the heat generation, as we explained during this video, is very, very important. And in high power applications, that's gonna be a very bad decision to use a linear regulator, which gonna be needing that heat sink and maybe air fan control, air fan cooling, which I don't recommend you do that. And of course, there is the steps down the voltage, but does not step up the voltage. Personally, I don't consider this to be a huge disadvantage, because you know exactly what you are doing by selecting a linear regulator. Because if you want to step up the voltage, there are other switching regulators mainly made for that. So to sum it up, use it for sensitive applications in terms of noise, such as analog to digital converters and stuff like that, audio circuits, if you want to need some nice audio quality. And make sure that the heat aspect of the design is very well designed and very well calculated. And besides that, do not use it for high power applications, as we have now switching regulators that can deliver really nice results and deliver some quality output in terms of noise. And finally, thank you all for following this tutorial to the end. Please share the video and like the video and subscribe to the channel. This really helps the channel grow. Please check my website thundertronics.net and visit my store and blog. And also please check PCBWay for all your PCB manufacturing stuff for hobbyists and for professionals alike. The link will be down below.